Okay, I hope everyone is able to hear me well, and I hope you're also able to see the screen all right. So we have been discussing, like I said, the postulates of quantum theory. State space, vector space identification has been done. The next thing which we discussed last time was how physical quantities or observables correspond to Hermitian operators, right? And we were discussing this with 3 examples of the so-called Pauli spin observables corresponding to the spin of a spin half particle. And we said that the spin can be probed along different directions. So there is a Pauli observable associated with the spin along the x direction, which was the Hermitian operator. So as we said, operators in these finite dimensional spaces essentially can be thought of as matrices, right? And then we looked at sigma z and sigma y, right? So these are 3 matrices which are all Hermitian, and they correspond to spin along different directions, right? The physical quantities that they correspond to spin along x, z, and y directions respectively. So what we were doing last time was to then go on to talk about eigenvalues and eigenvectors. And we said that one reason for associating physical quantities with Hermitian operators is the fact that, so we now get into a little bit of detail about Hermitian operators. So first of all, we said that an operator M is Hermitian if M is the same as its conjugate transpose. M is M adjoint. So these are also called self-adjoint matrices, right? And there are a few properties of these which makes them interesting from the point of view of quantum mechanics. So the first thing is, of course, their eigenvalues are all real, right? So what is an eigenvalue equation? So let me now write down an eigenvalue equation for some Hermitian operator n, right? So any vector or any state which is left invariant by the action of the operator up to an overall phase or an overall scalar is an eigenvector, right? So this is what we call an eigenvalue equation. Right? This is what we call an eigenvalue equation. So any vector which is left invariant by the action of the operator is an eigenvector or an eigenstate. Sometimes we even say eigenket, right? And the associated scalar is what we call the eigenvalue associated with that eigenvector, right? So now what one is saying is that the lambda are all real. So of course, a given matrix could have several eigenvalues and eigenvectors. So I could write some set of eigenvectors of this form associated with a particular observable or with a particular matrix. And the corresponding eigenvalues, I could denote them all as some lambda I, right? Then this set lambda I are all real for Hermitian matrices or operators, right? So how do we see this? One way to see this is, yeah, so does anybody know of a simple proof of this fact that Hermitian operators have real eigenvalues? Those of you who have done quantum mechanics.
We can take the dagger of both sides, right?
Okay, so let me
And
take the
then
dagger of both sides. So then I get, so remember, okay, so I don't know if, so when I take ME and I take the adjoint, so of course the way to show this would be to take the adjoint, right? Because this is the property that we've identified for Hermitian matrices, right? This is how we have defined Hermitian matrices, so that M is the same as M dagger. So when I take the dagger, right? So what happens? I have to switch the order of the product here in order for this dagger to be meaningful. Okay, so let me just note this as an aside. So when I have two matrices, let's say A, B, and I want to take their dagger, right? Then this becomes the dagger of the individual, the product of the adjoints of the individual matrices, provided you swap the order like this, right? Similarly, if I want to take this dagger, okay, again, this can be shown also, right? The way to show this would be to actually define, take the product, do the conjugate transpose, and show that it is the same as doing the conjugate transpose on the individual matrices, but reversing the order of the matrix product. Okay, so if you want to see proofs of all these statements, please look up Nielsen Chuang section chapter 2, sections 2.1 and 2.2 go over many of these basic linear algebra concepts and with proofs, right? Or at least indications of how to prove them. I just thought I could show the fact that lambdas are real very quickly. So then this becomes equal to E M dagger, right? And on the right-hand side, then we have E lambda star, right? So someone was helping me prove this. What was your idea? Who was it? Siddharth? I don't know. I don't know who spoke just now.
yes, ma'am, Siddharth.
Yeah. So what do you do next?
So now because M dagger is the same, also because we take a dagger now, so M dagger is still M, right? Because it's Hermitian.
Yeah.
And then just a second. So wait a second, just a second, sorry, just a minute.
Anyone else? How would you prove this? How would you
You
prove that the
can take
lambdas? Yeah.
you can take for the first equation M KPI, the inner product. You can have the inner product, right? So you can multiply it by bra EI for the first equation, and here for the second equation, multiply it by KTI. So that time, since M dagger is again M, you will have lambda equal to lambda star by taking the inner products of both the equations.
Okay. Very good. So this is 1. Okay. And this is 2. So now you're saying that here for 1, you can left multiply it by bra E, right? So that
That's
you have EME is lambda inner product of E with itself. Let's say it's normalized. It doesn't matter actually. You can even, whatever that is, that's a norm of E. And if I now do the right multiplication with the ket E for the second one, right, and use the fact that M is the same as M dagger. So I have this lambda star EE, but M is the same as M dagger. So then this must be the same as lambda EE, which then implies that lambda is the same as lambda star. Okay,
Ma'am,
good.
just one question here.
Yeah.
E could be a complex vector, right?
Yes.
So if we take the dagger, it should be conjugate of E, something like that, right?
Yes.
So we haven't done that here, have we?
What do you mean?
So if I take dagger of the entire equation, both sides,
Yeah.
I'll also have to take dagger of E. It's E, right?
So your question is about this, right? This E dagger, right? So
Right.
if I have some vector E in some representation, this takes complex numbers. I don't know, you can say A1, A2, etc., AD, right? Then what is bra E? Tell me.
Oh,
It's
it's
a row
okay.
vector
It's a raw
with
vector, right?
A1 star, A2 star, etc. Yes, this is exactly what I mean. So now what is your question?
No, okay. I was confused.
Yeah, that's what I mean by bra E. Now you see the point is this product. What can you say about this inner product? We already did this. What is the inner product of E with itself?
It has to be like sigma mod squared.
Correct, exactly. So it's of the
Norm of
form sum over I mod AI squared. So it's always, not only is it real, it's always positive. That's how we define that's how we could define a norm out of this,
right.
right? So it's a greater than equal to 0. It's equal to 0 if and only if this is the 0 vector, right?
Yes.
Yeah. Okay, so there is no issue with this argument, right? So because this quantity is always going to be a real positive quantity. So what this means is that lambda is equal to lambda star, right? I hope everyone understands this. So this is the first property, that the eigenvalues are all real. So when we make this association of physical quantities with Hermitian operators, then
Ma'am,
we say, yeah.
ma'am, the summation AI square, summation mod of AI square, of course it is greater than or equal to 0, but don't it is equals to 1?
If E is normalized. If E is normalized, it is equal to 1.
Okay.
Yeah, that's what this is the so-called norm of the vector, right?
Right.
This is the norm. And if the norm is 1, it is normalized. But I don't have to insist on that, is what I'm saying. Of course, that will make this even simpler. It will just be, you'll immediately get lambda star is equal to lambda, right? But yeah, I'm just saying that you don't even have to insist that it's a normalized vector. Okay, so physical quantities associated with Hermitian operators. The association actually proceeds by first noting that the eigenvalues, so the set of possible values of the physical quantities, of the corresponding physical quantities, they are the same as the set of eigenvalues of these Hermitian operators, right? And because Hermitian operators have real eigenvalues and physical, and if we want to make this association and make the correspondence between the values that the physical quantities can take and the eigenvalues, then you need to have matrices or operators with real eigenvalues, right? And the fact that these eigenvalues are real makes this association meaningful. So what does one mean by this? So let me take one of these spin matrices. Let me take sigma z, right? Of course, I have to put units, like I said, here, and the units are provided by this scalar multiple, which is h bar by 2 in the front. H is the fundamental Planck's constant, units of angular momentum, right? I mentioned all this last time. Anyway, I might forget to put the h bar sometimes. We physicists often put h bar is equal to 1, okay? So yeah, sometimes I may even forget to put the half, but please remember that these things are there. So let's keep the h bar by 2 now, and let's say you look at this matrix. So now what are its eigenvalues? I hope everyone knows how to compute the eigenvalue of a matrix. So let me just write down the so-called characteristic equation. So to solve for the eigenvalues of any matrix, I have to solve this equation, right? A minus lambda I, the determinant is 0, right? Okay, this is also called the I think Cayley-Hamilton equation, or yeah, anyway. So there's a characteristic equation to calculate the eigenvalues of a matrix. So what are the eigenvalues of this?
H bar by 2 and minus H bar by 2.
Indeed. So the eigenvalues, if I call them lambda I for this matrix, right? So you simply have to do 1 minus lambda minus 1 minus lambda, take the determinant, right? And set that to 0. So typically for a 2 by 2 matrix, this might give you a quadratic equation, right? So you will have two solutions to this. And of course, the eigenvalues of this are indeed plus minus H bar by 2. I know that a lot of you who have done basic quantum mechanics courses would have done all of this. The others, I encourage you to please work this out. And if you're finding any of this difficult, you have to stop and ask me, okay? Otherwise, I'll keep going on, right? And maybe this is already a little slow for some of the guys who have done the physics courses, okay? But anyway, I'm trying to find a happy middle ground here. All right, so now you will notice that in fact, all of these spin matrices have the same set of eigenvalues, okay? So all of these eigenvalues are indeed plus minus H bar by 2. Okay, same. So this indeed is the, this pair of values, the plus minus H bar by 2 are indeed the values that the spin angular momentum can take along any of these directions, right? And the corresponding eigenvectors, so this was the first property, right? The first observation that all these matrices have real eigenvalues, and so that's one reason why they're all useful to characterize physical quantities, right? The second property of Hermitian matrices or observables, which we will use, is the fact that the eigenvectors, so the second property is a property about eigenvectors. So those of you who already know this, who will tell me which what is the property that I'm talking about? What
Linear
can you say about the
independence.
eigenvectors? Yeah.
They are orthogonal.
Linear independence.
Okay, good. So I think I will take either answer here. The eigenvectors of a Hermitian operator, I will directly say are mutually orthogonal. Okay. Actually, I will say the property that I really want, which is that they form an orthonormal basis. Let me see. Okay, let me just say they are mutually orthogonal for now, and then we can form a basis out of that. Okay, so what does this mean? If I take a Hermitian matrix and I write down an eigenvalue equation like this, right? And now if I take two different eigenvectors, I not equal to j, corresponding to two different eigenvalues, right? Then this is equal to this is what I want to say. Yeah. Well, or it's at least proportional to delta ij, let's say, if I don't insist on normalization. So this delta ij is, of course, the Kronecker delta product, right? So this is 0 if I is not equal to j, and it is 1 if I is equal to j, okay? But suffice it to say that when I is not equal to j, so let me just say this is in general proportional to this the Kronecker delta function. So this is what is called the Kronecker delta function, right? But in particular, I want to highlight this property that when I is not equal to j, this is equal to 0, Okay. So the eigenvalues are all real, and the eigenvectors associated with different eigenvalues are mutually orthogonal, right? So again, can someone give me a quick proof of this? Is it possible to show this quickly? Okay, so think about this. So how will we show this? Think about this. If we have time at the end of class, I will show you. Otherwise, we can leave this as a homework. Maybe I'll actually put this in the assignment, right? So it's again a function of taking adjoints and writing down a pair of equations and showing that this inner product vanishes. So let's again look at concrete examples. Let's look at the sigma x. Actually, let's start with the sigma z, okay? So the sigma z was of this form. And I think last class we actually worked out the eigenvalues of this, the eigenvectors of this, right? So what are the eigenvectors of this matrix? Which are the eigenvectors? Did we not already do this last time?
Ma'am, Ket0 and Ket1.
Indeed, yeah. So the eigenvectors are what we call Ket0 and Ket1, the so-called qubit states, right? The basic qubit states. So let's just verify this. So I think what I did last time was to do this, right? That sigma z acting on Ket0 gives me plus h bar by 2 Ket0, and sigma z acting on Ket1 gives me plus h bar by 2, sorry, minus h bar by 2 Ket1, right? So 0 and 1 are indeed mutually orthogonal. They're also normalized, right? So this forms, like I said, an orthonormal basis. Remember, we've already seen this terminology, right? So the 0, 1 is what is often called the computational basis. Okay? Or the standard basis in as far as quantum computation is concerned. So similarly, let's look at the sigma x, right? Now, what are the eigenvectors of sigma x?
Plus state and minus state.
Indeed. Good. So again, you have another orthonormal basis coming out of this, right? So again, you can check this using equations like this. Sigma y. What are the eigenvectors of this?
Plus I state and minus I state.
Okay, very good. So these are actually the plus I and minus I states. So remember, we had defined this earlier. So plus minus I is nothing but 0 plus minus I1 by root 2, right? We had even marked these out on the block sphere, if you recall. So indeed, you can check that sigma y acting on plus I, plus minus I rather gives me plus minus h bar by 2 plus minus I, right? So these are indeed the eigenvectors of sigma y. They also form an orthonormal basis, right? They're mutually orthogonal and they're normalized, right? So the point is, if I give you a Hermitian matrix M with a set of eigen, so given a Hermitian matrix M with a set of eigenvectors EI like this, right? Then the set EI, someone said they're linearly independent. That is correct. Linearly independent vectors can always be orthogonalized, okay? And so I can essentially form an orthonormal basis for the linear vector space on which these Hermitian matrices act, right? So this becomes a very important feature of Hermitian matrices, because this then provides us a way to measure the operator, right? The fact that the different eigenvectors associated with the observable, and remember each eigenvector has an associated eigenvalue, right? This then provides us a way to measure the operator. And as we were discussing towards the end of last class, the fact that I associate an eigenvalue with an eigenvector means that in the state EI, the operator M, the observable M, has a definite value, right? And what do I mean by this? What is that definite value? That is lambda I, right? So this is what we said with the example of sigma z. We said that, for example, if sigma z has a definite value, the spin along the z-axis has a definite value in the state ket 0, right? And the fact that you can make a full orthonormal basis like this, right? Similarly, it has a definite value in the state ket 1. And these are the only two possible values that the operator can take. So this then provides us a way to describe a measurement of sigma z, right? So we'll describe measurement itself in the next class, on whether it's on Thursday or Friday, depending on when the holiday is going to be. But the next thing I actually want to do is then talk about diagonalization. Okay. Actually, let me first talk about outer product. And then diagonalization. So we have denoted observables as operators. In particular, I have associated matrices with them, right? Now, observables more abstractly are what? They are objects that act on states and transform them to something else, right? This is what generally an operator on a vector space is supposed to do, right? This is an operator, and these are states or vectors, right? Now, from this, how do we go to a matrix representation? I just told you that sigma z is this matrix, sigma y is that matrix, sigma x is this matrix, and so on. But how would you, in general, given, suppose I tell you the abstract action of sigma x, I say that sigma x flips 0 to 1. Now go ahead and identify the matrix representation of sigma x for me, right? How do you do that? So you know the action of the operator on some vector in the vector space, right? How does one get to a matrix representation from this? The key thing is to first note what the action of M on some basis is, right? So first we need to know what is the action of this operator on some orthonormal basis in the space, right? So let me say Vi is some orthonormal basis, okay? Let's say this is some d-dimensional Hilbert space. So I goes from 1 to d, okay? Let's say that this is a basis, right? When I say basis, I always mean an orthonormal basis, okay? So now what this means is, you know the action of M on Bi, right? But actually even this is really not necessary. What you can simply do is to expand these states psi and phi in terms of this basis, right? So once I have an orthonormal basis, so let me expand psi as some Ci Bi, right? And let me expand phi as something else, Si Ei, right? So then what do I have? I have this kind of an equation, right? I have M acting on sum over I, Ci Bi is sum over I Si Bi. Now what do I need to do? So how do I, so this is the thing, right? So this is what I actually need to get to, the action of M on some orthonormal basis in the space. So what do I mean by that? I need to extract out inner products of this form, right? So what is the inner product of, say, a basis element Bj with respect to M acting on Bi, right? So now this can be obtained by just taking this inner product here, right? So then I get, so this picks out something. So this is basically sum over I. Oops, sorry. So what I want to say is when I take this inner product here, I get something like this. So I get sum over I, Ci of this is Sj, right? So this in itself is not enough for me to get to these elements. So what I would then rather do is to look at this. This is what I started writing down earlier. So just look at the action of M directly on some basis vector. Now this could give me some arbitrary state. Let me call that chi, right? And that state would have some expansion of the form sum over j, cj, bj, right? So now I can get these matrix elements of this form, which is, so when I take this inner product, I'm just left with ck. Did I get that right?
No, why M, when M is applied on BI is the basis, so you will get the eigenvalue.
Okay, let me just
It's
back up a little bit. Yeah,
it's
so
not
let me,
chi, yeah.
I understand your confusion. Yeah, so the point is this, I said Bi is a basis, right? But I didn't say that M is a Hermitian operator. I said M is any operator, first of all, right? And I'm not working in the eigenbasis of M, okay? M is any operator. I'm not working in the eigenbasis of M. Bi is some arbitrary basis. I would like to write down a matrix representation for M, given the action of M on the states in the vector space. I said the thing you need is the, if you know what the action of M on some orthonormal basis is, then you can write down this matrix representation, right? And the reason for that is this. So maybe you can ignore the first 3 steps I wrote down. You can, if you wish, you can go through it, but this is the key part, that if I write down M acting on some element of that basis Bi, I get some other vector in the space, right? Of course, if it's a Hermitian, or I mean, if the Bi is the eigenvector of that matrix, I will get back some number times Bi itself. But in general, it's not an eigenvector. Does that answer your question, Yazid?
Yes, thank you.
Yeah. So it's not, I'm not talking about eigenvectors. I'm saying it's some arbitrary vector, but it's a basis vector, right? So that means I can expand whatever is the state after the action of the operator in the same basis, right? And I've just put an I on top here to denote that these are the coefficients you get when you act the operator on the ith basis state. So now I take an inner product of the kth basis state with this chi. So what have I taken here? I've said bk acting on chi, right? That's what this is, right? And chi is nothing but M acting on Bi. So this becomes an object like this, right? Now note that this is a number, first of all, right? So this tells me what the overlap of the action of M on one basis vector, right, is with another basis vector. It's the overlap of Bk with the action of M on Bi, right? And that gives me a number like this. Of course, note that there are how many such numbers? There are d squared such numbers, right? D squared such scalar elements, Cik, right? And these can be arranged into a matrix, right? So these can be arranged into a D cross D matrix where C11 is what? It's the action of M on the first basis vector, however you want to number your basis vectors. Its overlap with B1 itself. What is C12? It's the action of M on B1 with the overlap taken with B2, right? So on and so forth. So you can essentially populate this D cross D matrix in this form. And this indeed would give me the matrix representation of M. This is the matrix representation of M in the BI basis. Okay. So I hope this idea is clear, right? So rather than start with an arbitrary two vectors psi and phi, which is what I did here, this is not going to give me, this is going to give me an equation of this form, but I really want to get to these numbers, right? And these indeed will be my matrix elements, right? So these would be the matrix elements of M in this basis, the BI basis, okay? So you could, of course, do this simple exercise, right? So like I said, you know that sigma x acting on 0 gives me 1. Sigma x acting on 1 gives me 0, right? So what is the matrix representation of this? Well, I need to work out these 4 elements, right? 0x0. So what is this? 0x1, 1x0, and 1x1. Yes? So obviously this is 0, this is 1. What is 1x0?
1.
1, 0. Yeah, I hope you guys see this. So this then gives me the matrix representation 0, 1, 1, 0. So what I am writing down for sigma x is essentially the matrix representation in the 0, 1 basis, right? So this is 0, x 0. This is 0, x 1. This is 1, x 0, and 1, x 1, right? Is this idea clear? Okay, now let me ask you, what is the matrix representation of sigma x in the plus minus basis? So this, of course, comes with an overall h bar by 2. Okay. Yes, what is the matrix representation of sigma x in the plus minus basis?
Same as that of Z, like 1, 0, 0, 9.
Indeed. So I hope everyone sees that, first of all, sigma x will be diagonal in the plus minus basis, and its representation will basically be 1, 0, 0, minus 1 with an overall h bar by 2. Because what are the matrix elements now? They are of the form plus sigma x plus, but plus is an eigenvector of sigma x with eigenvalue plus h bar by 2, right? And this is going to be minus sigma x minus, and the cross terms are going to vanish. So this is the next point that I was coming to, which is diagonalization. So all Hermitian matrices will obviously be diagonal. The matrix representation, in fact, for any operator will be diagonal in its own eigenbasis, right? By which I mean the basis made out of its eigenvectors. Right? And since Hermitian matrices have orthonormal, so remember that I said that This is an orthonormal basis, right? That's what makes all these other terms in the superposition to go away. The fact that it's an orthonormal basis. So the fact that Hermitian operators, so the fact that it's Hermitian implies always the existence of an orthonormal eigenbasis, then implies that the matrix always has a diagonal representation in its orthonormal basis, right? So we say that Hermitian matrices are diagonalizable, okay? So this again is an important physical property. It's also an important property from the point of view of quantum information. Hermitian matrices are diagonalizable, which means you can always throw them into a diagonal matrix representation. You just have to identify the right orthonormal basis. Once you do that, the Hermitian matrix is diagonal with real diagonal values, right? So you can always have a representation of a Hermitian matrix of this form, right? Okay. Now, is there a way to represent the operator in the bracket notation? So far I've just done matrix representation. So how about representing these operators in the bracket notation itself, right? So remember, when I take a vector and when I take its dual like this gives me an inner product, right? Now instead, I can construct what is called an outer product, okay? Where I take the vector and I take a dual vector and I write them out in this order, right? So this is what I call an outer product. Now what does this give me? So remember that V is a column vector, right? Which is D cross 1. What is W, the dual vector? It's a row vector, right? So it's one row and D columns, right? Of course, it's complex conjugate and all that. So this is V1, V2, etc. V sub D. This is W1 star, W2 star, etc. WD star, right? So this is 1 cross D. So now if I again do the matrix product of this, what object do I get? Is it a number? Is it a vector? What is it?
Matrix.
It's indeed a matrix. It's a
D cross D.
exactly. It's a D cross D matrix. The first entry is V1 W1 star. The second entry is V1 W2 star, etc. The second row we populate as V2 W1 star, VD W1 star, and VD WD star. Right. So essentially, what I have is a D cross D matrix. This is V1 WD star. Okay, so the outer product thus represents a larger dimensionality object, and that is indeed operators on the vector space, right? So I hope you see the difference between these three kinds of objects. One is the vectors which belong to the vector space. Now, out of these vectors, you can make two kinds of products. You can make an inner product, which gives me a number or a scalar, right? This leads me to a number. And then you can also do this product, which is an outer product, which gives me a larger dimensionality object. It gives me a D cross D object for a D-dimensional vector space. This is no longer a vector in the vector space. Rather, it's an operator on the vector space. It's a matrix on the vector space, right? So, of course, now let's try to do the qubit example again. So let's look at outer products of this form. So let me look at the simplest outer products I can think of. The outer product of 0 with itself. What kind of matrix is this?
Projection operator.
Sorry? It's a 2 cross 2 matrix. What is the matrix? I want you to tell me what the matrix is.
It's a projection operator on ket 0.
Indeed it is. I will come to that
1
aspect.
0 0 0.
Indeed, yes, this is what the matrix is. So as somebody pointed out, this is indeed a projection operator. So what does one mean by that? So let's try to look at this. So if I gave you this as a matrix, that's one way of looking at it. But if I give it to you as this outer product, here's what you can do. You can act this on any arbitrary qubit state psi, right? So how do I act this on any qubit state psi? Now is where the bracket notation comes in very handy. This is a ket and this is a bra. And I'm acting it on some arbitrary qubit state psi. So this could, for example, be alpha 0 plus beta 1, right? So it's some arbitrary qubit state. So what does this give me? This part becomes an inner product. So this gives me 0 inner product 0 with psi. But inner product 0 with psi is a scalar, right? So this is nothing but 0 psi. This is a number. I can either put it after the vector, in front of the vector, it doesn't matter. But the point is, this operator has acted on an arbitrary qubit state psi and projected me to ket 0 itself with some number, which this number is basically what? Alpha, right? In this case. So the action of 0 0 on any state psi is to project psi onto 0. In fact, this is true for any state or any vector v, right? So I can construct a corresponding projection operator of the form ket v bra v, because the action of this on any other vector is basically to take the inner product of v with that vector and leave you with something which is parallel to ket v, right? Which is proportional to ket v, by which you mean that if you want to think of this as a direction in some abstract space, then you're along the vector v. This is exactly like how you would take an arbitrary vector in real space and project it down to the x-axis, or find the projection on the y-axis or the z-axis. So you take the inner product with the unit vector along that direction, and then you write the unit vector along that direction, right? That's how you take the projection. So that's exactly what is happening here. You take the inner product with respect to that vector, and then you write down the vector itself, right? So in general, for any vector, or rather for any state, right, I can write down a projection operator associated with that state, right? Okay, so 0 0 is a projection operator. What about 0 1? What kind of matrix is this? Now this is not a projection, right? Because this is going to take the inner product of the vector with respect to 1 and then give me a final vector which is along 0. So this is not a projection operator. In fact, it's going to take the component along 1 and give me and make that to be parallel to ket 0, right? But anyway, what is the 2 by 2 matrix for this?
0 1 0 0.
0 1 0 0. What is the 2 by 2 matrix for ket 1 0, ket 1 bra 0? Yes, what is 1 0?
0, 0, 1,
0,
0.
0, 1, 0.
Good. And what is 1, 1?
0, 0, 0, 1.
Indeed. Very good. And is this a projection operator?
Yes.
Right. So this is a projection along ket 1. Right. This is a projection operator which projects along ket 1. Right. So now notice that I can write down the following. So if I take the projection along 0 plus the projection along 1, what do I get? So I want you to identify these matrices for me now. If I take the projection along 0 minus the projection along 1, what do I get? If I take 0, 1 plus 1, 0, what do I get? Yes, what's the first one? 0, 0 plus 1, 1?
Identity.
Indeed. Can you just tell me the matrix? 1,
1,
0,
0, 0, 1.
0, 1, right? And this is the 2 cross 2 identity matrix. Okay. Now this is an important property of an orthonormal basis. It is what is called a completeness relation. Okay. So what is this? So if I take, so if BI is an orthonormal basis for a vector space, then if I make these outer products, which are nothing but projections on BI, okay, and I sum over all of them from 1 to D. So let's say that this is a D-dimensional linear vector space, right? Then this essentially gives me what? The D cross D identity matrix. Okay. So this is another crucial property of an orthonormal basis. And again, you can easily check this by taking this left-hand side, taking the inner product on both sides appropriately with the ket and the bra, and you will notice that this is indeed the identity matrix, right? Okay, now what about the second sum that I wrote down of these two outer products? 0, 0 minus 1, 1. What matrix is this?
1, 0, 0, minus 1.
What is that?
Pauli Z matrix.
Indeed. So it's basically the sigma z up to an overall h bar by 2, right? And this basically is a diagonalization equation, right? So this is the next thing. So if I have a Hermitian matrix M with, so this is Hermitian with eigenvalues lambda I and corresponding eigenstates EI, then this is what the outer product representation of the matrix looks like. Since the matrix is diagonal, right? Remember I said the matrix has a representation of this form where it's diagonal, right? It has lambda 1, lambda 2, etc. up to lambda d sitting in the diagonals. Everything else is 0, right? So what kind of outer products does this mean? In its own orthonormal basis, it's diagonal. What are the outer products corresponding to each of these locations? This is lambda 1 times E1, E1, lambda 2 times E2, E2, etc. So this basically is the diagonal form in the outer product notation, right? So this is what we have done here actually for sigma z, right? So if I put this factor of h bar by 2, it's basically h bar by 2, 0, 0, minus h bar by 2 outer product 1, 1. But 0 and 1 are essentially the eigenstates of sigma z, right? And the corresponding eigenvalues are plus minus h bar by 2. So indeed, if I take a Hermitian matrix, I take its eigenvectors and eigenvalues and I form these outer products. Now note that these are all actually projections, right? They are outer product of a vector with itself. So they're all projection operators, right? For all the entries of the diagonal, the corresponding outer product operators are all going to be projection operators, right? So I basically make the projections onto the eigenstates and sum them weighted by the eigenvalues. I get the diagonal form of the matrix itself, right? Okay, the final thing, what is 0, 1 plus 1, 0? What matrix is that?
Sigma X matrix.
Indeed. So this is the matrix of the form 0, 1, 1, 0, right? So if I again put an h bar by 2 here, then this is sigma x. Okay. Now I leave you with this question. What is the diagonal outer product representation for sigma x? So let's stop here. So how will you write down the diagonal outer product representation for sigma x? Okay, so what we've done today is to go over properties of Hermitian matrices in some detail. And also write down the diagonal representation and write down the outer product representation. We've also seen in the process how to write a matrix representation for any observable, right, in terms of the bracket notation. Questions?
Ma'am, it's not exactly the sigma x operator, right? Because we are not considering the factor of h bar by 2 here. It's actually the x matrix basically.
Indeed, yeah, you can call this the X matrix. Yes, I just said, yeah, since today we've been discussing fully observables, so I just put the h bar by 2 to call it sigma x. That's all. Yeah, just by itself, this is what we call the X gate or the NOT gate, right? Yeah, indeed. Questions? Yeah.
Hello. How can we interpret this outer product of ket 1 and ket 0? Like ket 0, ket 0, bra 0, or ket 1, bra 1 can be interpreted as projector. So how can we interpret this ket 1, ket 0 type entity?
So this then tells you exactly what this does on a particular state or a particular thing, right? So suppose I take the complete matrix, which is 0, 1 plus 1, 0, right? And let's say I act this on ket 0. What does it do? The action on ket 0 gives me, it takes ket 0 and gives me ket 1. This part doesn't contribute. It actually destroys the ket 0 completely, right? So you have to do this term by term. So let's do the first term. So this is 0, 1 acting on ket 0 plus 1, 0 acting on ket 0. 0, 1. So this inner product goes away. This inner product is 1. So it gives me 1. So this tells you that this is actually flipping the 0 to the 1, right? More generally, if I put an arbitrary ket psi here, right? So if I do this plus 1, 0, acting on an alpha 0 plus beta 1, you should be able to check that this gives me alpha 1 plus beta 0, which is exactly what the X operator is supposed to do, right? So it takes the component of the vector parallel to 0 and then projects it onto 1 actually. This part takes the component that is parallel to 1 and gives me something which is parallel to 0, right? So these kind of terms are what you will call the off-diagonal terms in any matrix representation. And that's why this X matrix is a fully off-diagonal matrix. It has no diagonal terms. It's fully off-diagonal, right? Yeah. So the outer product notation tells you the action of it's basically an operator which takes something which is parallel to this dual part and projects it onto whatever is in the primal part. And that's one way to think about it. Right?
So ma'am, this projection of, let's say, one state on the 0 state, which happen to be mutually orthogonal, is not vanishing because they are essentially, um, parallel to each other. They are not exactly 90 degrees apart in the block sphere. Had they been 90-degree apart in the two-dimensional real space, they should have vanished, right? We are projecting one state onto its orthogonal state. It should have been a 0 component, right?
You mean this part 0, 1 acting on 0? Is this what you're talking about?
Yes, ma'am. Yes, ma'am.
Indeed 0. This is indeed 0, right? That's what I said. I said this term goes away. The first term goes away and gives me 0. It's only this term which survives and gives me 1. This term is 0.
Ma'am, I'm talking about, let's say we have the outer product of 0, 1. This thing acting on a psi state. The way we are projecting the component of one, let's say ket1 on the ket0 vector. This thing acting on psi state.
No. So maybe when you misunderstood what I said. This is not a projection, right? This kind of an operator is not a projection operator. First, let's be clear about that. I just said it picks out a component which is along something and makes it into something else. So this is a transformation, right? It's a transformation which is not a projection, right? So if you want to think in terms of your real three-dimensional vectors, it's like I have a vector v, which is vx I cap plus vy j cap plus vz k cap. It's like I take the k cap component and then I assign it to I cap, right? That's a transformation of the vector. It's not a projection down to a particular axis. It's transforming the v vector into something else. The way it's doing the transformation is a particular way. It's taking some particular component of this and putting it somewhere and so on. Right? So it's a transformation. It's not a projection.
Okay, ma'am. Okay, ma'am. Thank you.
Yeah. Any other questions? Okay, so no more questions. Then I'll meet you on Thursday. You might have the assignment uploaded by then. And yeah, I don't know if anybody answered this question already. What is the diagonal outer product representation for sigma x? Yes, anybody? Okay, so think about it, and maybe next class we'll start with that. Okay.
Sorry, can you repeat the question, ma'am?
How would you write down a diagonal outer product representation for sigma x?
Oh, okay.
We saw a diagonal form for sigma z, right? Which is 0, 0, minus 1, 1. Right? And, yeah.
It will be plus, plus, minus of minus, minus.
Indeed. Very good. So the answer is indeed, it will be up to the h bar by 2. It will be plus, plus, which is a projection on plus, minus, minus, minus. Right? Indeed. So like I said, for any Hermitian matrix, The outer product diagonal representation is simply take the projections onto the corresponding eigenstates and then weight it by the eigenvalues, right? And these eigenvalues are plus minus h bar by 2. So this would be the outer product representation for sigma x, which is diagonal, right? Okay, so let's stop here and I'll see you all on Thursday.